Okay, today we're going to talk about distances, but before we do that, we're going to talk about number 15, because I said I would. All right, here's the diagram, and part A asks to find a unit vector between these 2 points, and that's over here. But we're not going to use that unit vector for the equation of the line, or the line, because it just makes things harder than it has to be. We're going to use this vector, and you should have come up with this for the line. I wouldn't use that unit vector. It just overcomplicates things. All right, part D, though, was a little bit... They ask you, okay, how do you know this normal vector? And they give it to you. They gave the normal vector to the plane, and I think in my diagram the plane was yellow, by saying, if you go to this point and move 6 units parallel to the x-axis and then 6 units parallel to the z, you get to that point up there, which wasn't named, I don't think, but it is 6014. Now, there's no y-coordinate there. This entire section, that triangle and that rectangle, lie on the xz plane. So they can't possibly be a j component to this normal vector, because it has to be in this plane. All right, let's look down here. And if I look from this perspective, from the y-axis looking back toward the origin, I see this picture where the positive x-axis is actually pointed to the left. All right, so if I find a segment between 008 and 6014, that segment has a slope of 1, positive 1. Now, it doesn't look like a positive 1 because, keep in mind that, normally we see the x-axis pointing in to the right. But this isn't the xy plane, this is the xz plane, and we're looking at it from this direction. All right, now, if anything that's perpendicular to that segment would have to have an opposite reciprocal. So the normal vector would have to have a slope of -1, in which case I'd have an x component of -1 and a z component of +1. It could have been 1 and -1, and that, in which case it would be pointing in that direction, but I have it pointing like this. Now, if this is in general, and this is another technique you can use, is that if you know a vector and you want to find a vector perpendicular to that one, I'll erase this for just the time being, that you know that this dot product, and they gave you this vector, let's say this one is 6i plus 6k, that vector. What's a vector that's perpendicular to that? Well, the dot product has to be 0. So this number times something plus this number times something else is equal to 0. Now, the only time if these two are equal, then these two numbers are going to have to be opposites. And the easiest thing to put in there is a -1 and a +1. I could have put in -10 and +10, or -100 and +100. That would just overcomplicated things. That's why this normal vector is what it is. Now, you should have been able to do this part, because they even gave you that normal vector. All right. Today's topic is distance between point and plane. Actually, let me put this up here. I have posted this document for you. And it's a formula sheet for everything in chapter 12. These ones you're familiar with: dot product, projections, and cross product. Projection's going to come up today, by the way. And distances, okay, this is point and plane we're going to talk about today. Point and line, and skew lines is going to come up later. Volume of tetrahedron will come up today. So that is there for you. And one thing we haven't done throughout the shutdown is too much theory. Now, the question, and that's today's topic, is why is that formula? Why does it end up the way it does? Well, we're going to talk about that today. We're going to do that. We're going to derive that formula. And if you don't want to watch it, there is something in here that you'll need to know in order to answer the question tonight. So, just warning you. All right, so let's say that we have a plane, and we'll call that plane M, and the equation of that plane M is ax plus by plus cz is equal to d. And let's assume that this plane, we're looking at it so that it, the origin is behind it if I would have extended it. All right, and then we have a point P0 that's not on that plane with coordinates x0, y0, z0. Okay, now the shortest distance between this point and that plane is going to be at a perpendicular. Let's say here, on a line. Let's say there's a line that passes through this point and hits this plane at a perpendicular. All right, now a good way to draw these perpendicular symbols is the one segment of the perpendicular symbol should be parallel to an edge of your plane, and the other one should be parallel to the other edge of the plane you drew. Okay, so that's this line, of course, will continue. The point lies on a line that's perpendicular to that plane. Okay, now the normal vector to this plane, it's got to be parallel to that line, obviously, and I could draw it anywhere. I could draw it there. I could also draw it in the other direction, pointing in the other direction. I'm not going to do that. Okay, now any point on this plane M, a variable point, we'll call it x, y, z, meaning I could have put that point here, I could have put it here, I could have put it anywhere on that plane. If it has variable point or variable coordinates x, y, and z, it has to follow this rule: ax plus by plus cz is equal to d. But it could be anywhere. All right. Now I'm going to redraw this, but it's not going to look the same. This is plane M. Now there's always a perspective to be gained in space where you're looking at a plane and all you see is a line, because you're looking at it and the plane has no thickness. You're looking at this plane like your eye level is at plane level, and you're looking straight down the plane. You just see a line. All right, and the point P0 is not on the plane. Here's the line that I was talking about that travels, or that P0 is on that line, and it's perpendicular to the plane. And I could put the variable point P anywhere. Now this point P has coordinates x, y, z, and remember they're variable points because it could have been here, it could have been here, it could have been anywhere. Now this one's fixed: x0, y0, z0. Any subscripted point has known coordinates. Okay, we have a vector between P and P0, that's vector P, P0. And we also know that the normal vector is perpendicular to the plane. This vector has some length, and the magnitude of that is the square root of a squared plus b squared plus c squared. Now, if you recall, this distance that we're looking for right here is the scalar projection of PP0 onto n. Now, when we drew this before, we had them tail to tail, and you can redraw that. It's really not necessary, but you take my word for it that this distance is the scalar projection of PP0 onto n. All right, so that distance we had a little formula for this, and it's on the formula sheet. That's PP0 dot n over magnitude n. Okay, now vector PP0. Now how do you get it? End point minus beginning point. So that is x0 minus x I, y0 minus y j z0 minus z. Okay. Now n, of course, is ai, bj, ck. All right, so pp0 dot n is equal to, and I'm going to do a couple things at the same time, ax0 minus ax, by0 minus by, cz0 minus cz. All right, so that is regrouping a little bit. You got ax0 plus by0 plus cz0 minus the quantity of ax plus by plus cz. Ax plus by plus cz is d. So that makes this distance, now I'm going to put a little bracket thing there, that's d. The distance then is ax0 plus by0 plus cz0 minus d over magnitude n, which is the square root of a squared plus b squared plus c squared. All right, going back to my little formula sheet. Up here, we have symbols. And we usually play a game about this in class, but we can't do it this year. Question is that a magnitude or an absolute value? Well, in this case, it has to be absolute value because none of this stuff is vector. That's a dot product. That's not a vector. That's a magnitude. That's a number. All right, so this is an absolute value. The question is, why is that absolute value there? Well, the reason the absolute value there is because that dot product could be positive or negative. Let me get myself in the frame, the proper frame here. Okay. Well, how do you know that? All right, well, here's a redraw again. Here's M. And let's say that there's the origin. And here's our P0. Okay, well, there's the normal vector that we're talking about. And here's PP0. Now, if I displace this and actually put it tail to tail, that scalar projection, this angle right here is acute. All right, so if we have an acute angle here, that dot product that I was talking about on the other side of the paper is a positive number. On the other hand, if I have this situation, here's our little origin thing, here's M, and let's say P0 is over here. There's PP0 and here's N. Now if that angle between them is obtuse, then that dot product's negative. There's a slight problem with this analysis is the normal vector can be pointed any way. So what we do is we define the positive normal vector as the vector that's pointing away from the origin when you know, on the normal vector to the plane is pointing away from the origin. And how do you know it's a positive normal vector? Well, that's kind of hard, actually. And we spent quite a bit of time on this in class with my visual aids of the 3D coordinate system. There's no way I could do that here. So I'm just going to tell you. You find the positive normal vector by make sure that the D in the equation of the plane is positive. You know, for example, we have one of our homework, one of the example problem we're going to do here in a second is this D is negative. Well, you got to change that d to positive, and then you can get the positive normal vector. So the positive normal vector is defined to be the vector that points away from the plane. In order for this analysis to work, we got to know the positive normal vector. Now, to know the positive normal vector, you make d positive. All right, you might say, okay, what are you talking about? Here's an example. So I have posted a document. It says extra problems for chapter 12. Here's the document. Okay, here, this is going to be problem number 2A. And it says, given a plane, 3x minus 7y plus 5z is equal to negative 13, and a point, 5, 2, 1. Find the distance between that point and that plane. And moreover, the question asks, tell me where that point is in relation to the plane and the origin. Is it on the same side as the origin is to the plane, or is it on the opposite side from the origin of the plane? And you know, basically a plane divides space into two regions. One side of the plane and the other side of the plane. Now, where is this point in space with relation to the origin? And that's an important information at times. Now, I guess there is a situation where that wouldn't occur, as if the plane contained the origin, in which case this would be a 0, so this condition wouldn't apply. All right, well, anyhow, this plane has a negative number here, so an identical plane to this is negative 3x plus 7y minus 5z is equal to positive 13. The positive normal vector is found when that value is positive, so that would be negative 3i plus 7j minus 5k. Okay, so the distance, this is a very, very easy thing to do. The distance is absolute value of negative 3 times 5, negative 15, 7 times 2, 14, negative 5 times 1, negative 5 minus 13 over the square root of 3 squared plus 7 squared plus 5 squared. Okay, so that is, see, I have this written down here so I don't do any mental math errors. Maybe I don't have it written down. No. I apologize for my delay tactics. Okay. Well, let's just do the mental math. Negative 1 minus 6 is negative 19 over 49, 25, that's 74 plus 9, a squared of 83. Hope I didn't make any mental math errors. All right, now so the distance itself is 19 divided by the square root of 83, but this negative sign in here, what's it tell us? I'll go back to the diagram that we just drew, if I can actually find that one. If it's a negative, that means that the point has to be on the same side of the origin. This point is on the same side as the origin to that plane. Okay, so the answer here is same side as the origin. All right. Question 2b asks that as well. It says here, find whether this point's on the same side or the opposite side. All right, so you do problem 2b. Okay, another problem that you have to do is problem number 4, which is find the volume of the tetrahedron formed by these 4 points. Okay, well, this is a multi-step process to find the volume of a tetrahedron. First thing you do is you find the area of this triangular base, and in the this document online, you get a little bit better picture because it's colored in. Okay, so you find the area of the triangular base. I'm just going to leave that up there. And you do that by techniques that we've already talked about. You know, you take the cross product of, say, AB with AC, and the area is 1/2 the magnitude of AB cross AC. Then, and this doesn't look so good in here, but the perpendicular height from point D to that plane is the height of the tetrahedron. And you find that by finding the distance between this point and the plane formed by those three. Well, how do you do that? Well, you need the equation of the plane formed by those 3 points, which we have done. You find the equation of the plane formed by the 3 points, then you find the perpendicular height. The volume of a tetrahedron is 1/3 times the area of that base times that height. So that's how you form the volume of a tetrahedron. An interesting fact is, if all of the points, and there's good reason for this, and you can, as you go through this, you might be able to spot it. If every point of the 4 points that form a tetrahedron have rational value coordinates for all the coordinates, then the volume of the tetrahedron is a rational number. So you should get a rational number for this volume for problem number 4. And it's not a complicated number. You'll see it when you get it. Okay, so it should come out as a rational value. All right, well, I do apologize. I don't think this is anywhere near what I could give you if we were meeting in person, but that's those are the limitations we have. If you have questions, post them. All right.